Ever wondered how your electronic devices work at the atomic level? It's all about semiconductors. These fascinating materials, with their ordered crystalline structure, derive unique electronic properties from the world of quantum mechanics. Picture a lattice of atoms, neatly arranged, each playing its part in the grand symphony of electronics. Now, let's delve into the band theory of solids, a concept deeply rooted in quantum principles. In this theory, we visualize the distribution of electrons across different energy bands. Two notable players here are the valence and conduction bands. The valence band is densely populated with electrons, while the conduction band, higher up in energy, is relatively empty. However, these bands don't exist in isolation. They're separated by a region known as the bandgap, a forbidden zone where electrons cannot exist. The size of this bandgap is critical. If it's too wide, electrons can't make the leap from the valence band to the conduction band, and we have an insulator. But if it's just right, we get a semiconductor, a material whose conductivity we can control. In semiconductors, when the temperature rises, electrons gain enough energy to jump the bandgap and move to the conduction band. This leaves behind vacancies or holes in the valence band. These electrons and holes, both of which can carry charge, are the key players in semiconductor devices. But how do these electrons and holes move around? They do so in response to an external electric field, hopping from one atom to another. This movement or current is what powers your electronic devices. So from the atomic arrangement to the behavior of electrons and holes, it's the principles of quantum mechanics that choreograph this dance of charges. This intricate interplay dictates the semiconductor's conductivity and response to external stimuli. It's fascinating, isn't it? How the tiny particles, governed by the peculiar laws of quantum mechanics, can have such a profound impact on our everyday life. But what differentiates one semiconductor from another? Well, the answer lies in the distinction between intrinsic and extrinsic semiconductors. Intrinsic semiconductors are distinguished by their inherent purity. They are virtually free of any impurities, and their electronic properties are governed solely by temperature-induced thermodynamics. They're like the pure, untouched snow on a winter's day. On the other hand, we have extrinsic semiconductors. These are the rebels of the semiconductor world. They undergo intentional modifications, a process known as doping. Think of it as adding a dash of spice to a recipe. This process introduces specific impurities into the semiconductor, such as phosphorus or boron. These impurities can dramatically alter the electronic properties of the semiconductor, tweaking its behavior to our liking. The magic of extrinsic semiconductors lies in their versatility. They can be tailored to suit a wide range of applications, from microprocessors to solar cells. So in essence, doping introduces specific impurities like phosphorus or boron, altering the semiconductor's properties. How does temperature affect a semiconductor? Let's dive deep into the Fermi-Dirac statistics to understand this. The Fermi level, a concept rooted in these statistics, signifies the energy state at which electrons have a 50% probability of occupancy. This fundamental parameter plays a pivotal role in dictating the semiconductor's conductivity, making it a critical factor in the functionality of electronic devices. Now, the story doesn't end here. We also have another player in the game, carrier concentration. This dynamic quantity, influenced by temperature variations and doping concentrations, exerts a profound impact on the semiconductor's electrical behavior. When the temperature rises, more electrons gain the energy to jump from the valence band to the conduction band, increasing the carrier concentration. Similarly, doping, the process of adding impurities, can also increase the number of charge carriers. This intricate interplay between the Fermi level, temperature, and carrier concentration reveals the probabilistic nature governing electron occupancy. What happens when an electric field is applied to a semiconductor? That's where the fascinating world of charge carriers comes into play. Charge carriers, which include electrons and holes, are the unsung heroes of electrical conduction in semiconductor devices. They're the ones that get things moving, literally. Now let's talk about carrier mobility. This isn't just about how fast these carriers can move. It's an intricate parameter governed by a multitude of factors. Think scattering mechanisms, quantum phenomena, and even the vibrations of the crystal lattice itself. Yes, you heard it right. Even the tiny oscillations of atoms in the crystalline structure of semiconductors can influence the mobility of charge carriers. So when an external electric field is applied, these charge carriers zip through the semiconductor material, their speed dictated by their mobility. This makes carrier mobility a critical player in the electrical performance of semiconductors. And let's not forget, quantum mechanical intricacies contribute significantly to the overarching performance of semiconductor materials. How do semiconductors interact with metals? That's a question that brings us to the fascinating realm of metal-semiconductor interfaces and semiconductor junctions. At the intersection of metals and semiconductors, we encounter Schottky diodes. These devices are the result of a unique interplay between quantum mechanical phenomena and charge transfer dynamics. When a metal and semiconductor come into contact, the electrons move from the semiconductor to the metal, resulting in a barrier at the interface. This barrier, known as the Schottky barrier, gives rise to the rectifying properties of a Schottky diode. Its fast switching speeds make it advantageous for many applications, including in power converters and radio frequency applications. But what about when we need a low-resistance connection between metals and semiconductors? Enter ohmic contacts. Unlike Schottky contacts, ohmic contacts allow for efficient charge flow across the metal-semiconductor interface. Achieving an ohmic contact involves careful material selection and precise fabrication techniques to ensure that the energy barrier for electron transfer is low. This is crucial in device applications where minimal energy loss is desired, such as in transistors and integrated circuits. But the marvels of semiconductor science don't stop at the interface. Let's delve deeper into the heart of the semiconductor, where we encounter semiconductor junctions. These junctions are especially interesting when they're heterojunctions, interfaces between two different semiconductor materials. By juxtaposing two distinct semiconductors, we can engineer a myriad of electronic properties. For example, the bandgap difference between the materials can be exploited to create devices like light-emitting diodes and laser diodes. So, from Schottky diodes to ohmic contacts and from semiconductor junctions to heterojunctions, we see how the interplay between metals and semiconductors shapes the electronic properties of devices. These interfaces and junctions provide a rich landscape for creating bespoke electronic devices. Can we manipulate the properties of semiconductors? The answer lies in the fascinating world of quantum confinement and bandgap engineering. As we delve into the nanoscale domain of semiconductors, we encounter a realm where quantum mechanical principles reign supreme and the conventional laws of physics take a back seat. Here we encounter structures like quantum dots, quantum wells, and nanowires, which are engineered to exhibit unique properties. Quantum dots, for instance, are tiny particles that confine electrons in 3 dimensions. This confinement, aptly termed quantum confinement, leads to fascinating phenomena. It allows precise manipulation of electronic states, taking us one step closer to the tantalizing prospects of quantum computing, advanced sensors, and efficient energy harvesting. Quantum wells and nanowires, on the other hand, confine electrons in 2 and 1 dimension respectively. This confinement leads to quantized energy levels and results in a plethora of intriguing properties that are exploited in a range of applications, from lasers to transistors. Then, there's bandgap engineering, a sophisticated process that takes us on an exploration into the very heart of semiconductors. This process involves making deliberate alterations to the band structure of a semiconductor to meet specific device requirements. It's like having a palette of electronic properties at our disposal, ready to be tuned and tweaked to perfection. By manipulating the bandgap, we can control the energy required for an electron to jump from the valence band to the conduction band. This manipulation affects the semiconductor's light absorption and emission characteristics, enabling us to create devices that operate at different wavelengths. Imagine, for instance, an optoelectronic device that could be tuned to operate at any wavelength, from infrared for night vision devices to ultraviolet for sterilization applications. That's the power of bandgap engineering. In essence, through quantum confinement and bandgap engineering, we can tailor-make semiconductors to behave exactly how we want them to. This allows for the tuning of bandgaps for different wavelengths in optoelectronic applications. So, where are we headed in terms of semiconductor research? While silicon remains a cornerstone in the world of semiconductors, the frontier of advanced applications is being carved by compound semiconductors. Gallium nitride, or GaN, and silicon carbide, known as SiC, are emerging as potent contenders. GaN boasts a substantial breakdown voltage and high electron mobility, making it ideal for power electronics and radio frequency applications. SiC, with its high thermal conductivity and bandgap, is perfectly suited for high power, high temperature, and high frequency conditions. These compound semiconductors, with their unique characteristics, are paving the way for the next generation of electronic devices, from electric vehicles to renewable energy systems and beyond. Indeed, the synergy between crystallography and quantum mechanics will continue to shape the landscape of semiconductor research, fostering innovation and progress. As we delve deeper into the quantum realm, the future of semiconductor research promises exciting developments in the field of electronics.